Okay. All right, so we started talking about alkenes. We kind of introduced that new functional group, and what was so special about that functional group is they have a lot more reactions. They're a lot more reactive than just alkanes, right? And we talked about how that was all about that carbon-carbon double bond, specifically because of the geometry of that bond, as well as the fact that the second bond is that pi bond. So not only is that double bond really accessible in that molecule. It's this flat region where other molecules can get to very easily. But it's also got all that electron density sitting right out there in the open, right? So what we said is we kind of introduced this idea of nucleophiles and electrophiles, how nucleophiles attack electrophiles. And we said that our carbon-carbon pi bond can play the role of a nucleophile in reactions. Okay, and specifically what we were looking at what are called addition reactions, or I guess specifically nucleophilic addition reactions. Electrophilic addition reactions, sorry. We're adding electrophiles. All right, where if we take that carbon-carbon double bond, so we're just going to use a very simple example here. And we treat it with one of those hydrohalic acids. So for example, HBr. All right, everybody take a second. Remind me what the product is of these reactions. Okay, our carbon-carbon double bond, that pi bond gets broken, and instead I get two new single bonds on either side. One to the H of the HBr, and the other to the Br of the HBr. All right, and I still have my other hydrogens. On those carbons. And we even went as far as to look at the reaction mechanism of this reaction, and we're going to kind of revisit that here today as well. This is what is called a hydrohalogenation reaction. All right. Another addition reaction that we're going to talk about is what's called a halogenation reaction. If we take that same alkene substrate, but now this time, instead of reacting it with a hydrohalogen, we're going to react it with just a halogen, one of our diatomic halogens like Br2. All right, and in analogy of what we were doing above with our addition reactions, I want you to try to predict the products of our halogenation reactions. All right, what do we think our product will be here if we do an addition with Br2 instead of HBr? All right, we're again going to break that carbon-carbon pi bond. We're going to get two new single bonds on either side, but this time, what are my single bonds bonded to? They're both going to be bonded to one of those bromines. All right, so just like before, one of those gets added to one side, the other gets added to the other side. Let me go ahead and fill in my hydrogens here. Okay? So these are these two addition reactions that we're going to talk about in depth today. A hydrohalogenation reaction where we're adding a hydrohalogen like HBr, and a halogenation reaction where we're adding a halogen. Remember, our halogens are diatomic. So this is Br2 here. I'm just showing that Lewis structure of that molecule. And just like before, we're breaking that carbon-carbon pi bond, and we're making two new single bonds on either side, adding those two elements. Okay, so let's just practice this real quick. We were looking at very simple substrates, ethene, the smallest possible alkene that we could have. Now let's do the same thing looking at some larger substrates. Okay, we're just going to practice. Okay, so give me the product of this reactant, this substrate here with HBr. And then the same thing with Br2. I'll pick a new substrate here, and we're going to do those same two reactions. All right, so let's do this one together here. I'm going to kind of color these carbons so we can keep track of who's who. I'm going to color one in orange and one in green. All right, when I'm going to do my products, I'm going to make sure that I have the same number of carbons on both sides. In fact, the most important double check for you to do when you're done drawing your products is to go back and count carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Make sure you have the same number of carbons on both sides, all right? Counting carbons is a really easy double check to make sure that you're not going to lose points for something stupid. And if we're HBr, then what am I adding to one side? The H. What am I adding to the other side? The halogen. So H and Br. I'm going to look to my next reaction here, and I've got something very similar, same substrate, so I should again have those 6 carbons. But now I'm adding a bromine to one side and a bromine to the other side. All right, and again, what's my double check that I'm going to do? Count carbons, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Always count your carbons. Okay. One thing to note about this hydrohalogenation reaction, I drew in those two new bonds explicitly, but did I have to include that hydrogen there? No, right? So I could have also drawn the product of my reaction like that, and that would have been perfectly fine. What's up?
Can we have switched places? Like the bromine?
Yeah, so this is kind of where I'm going. In this case here, you can convince yourself that if you did switch places, this is the exact same thing, right? I would count from this way, 1, 2, my bromine's on carbon 3. If it was the other way around, 1, 2, 3, my bromine's on carbon 3, right? So those are the two exact same things. It's going to be a little bit different, and that they're the exact same thing because I have this symmetric alkene here, okay? Down here, it's going to be a little bit different of a story. So first of all, let's do this first reaction here. Again, I'm going to color these two carbons, one of them orange, one of them green. That means I should have 4 carbons in my product as well. All right, and for my halogenation reaction, does it matter which carbon I pick to put my bromine on? No, why not? Because I'm putting the same thing on both of them. Right, so here's a bromine here. Here's a bromine here. Let's say this is my blue bromine and this is my red bromine. Do I have a different product if I have these two switch places here? No, this is the exact same thing. Okay, so let me just also note real quick about drawing our products. I drew this bromine one up and one down, kind of the same thing that I did over here, but because it was on the end, I could have also pointed it over here. And this is the exact same thing, right? Because we can rotate about all of our single bonds, so I didn't draw a different structure by pointing that in a different direction. All right, but here, now we have a little bit of a tricky problem. Because again, if I color my carbons, one of them orange and one of them green, I know I'm going to add hydrogen to one and bromine to the other. But if I add my hydrogen to the orange carbon and my bromine to the green carbon, I would get a different product than if I switched those two groups, right? Since they are no longer identical, all of a sudden my product ID will change depending on where I add those new bonds. All right. So this is what's called regioselectivity. And where we're going to go is which one of these is going to be our products. All right, it turns out that only one of them is our actual product. That's kind of what we're working up to here. But this is what's called a certain feature that we have to watch out for with certain reactions, what's called regioselectivity. All right, a regioselective reaction. This is a reaction where new bonds are formed in a particular place, all right, a particular region of your substrate. All right, an example of a reaction, let's start with the best case first, which is not regioselective, are those halogenation reactions. All right, and we kind of convinced ourselves of that with our last example. I'll put an even simpler one down here. We'll pick a different halogen just for fun. Now we'll do chlorine. In this reaction here, regardless of which side of my double bond I pick to add my first chlorine, all right, we'll color this one in red and this one in blue. If I were to pick those two chlorines up and have them swap positions, I haven't actually created a new molecule here. These are the same thing. So this reaction is not regioselective. It doesn't matter which bond I put where. And as we said, it's not regioselective because both new bonds are identical. Okay? So then an example of a reaction that is regioselective, where we are going to have to worry about this, is our hydrohalogenation reaction. If we take that same substrate and we play that same game, but this time we're going to use HCl. We would get a very different product if we put that hydrogen on the first carbon and the chlorine on my green carbon compared to the chlorine on my, really the second carbon, and my hydrogen on that green carbon, right? So these are now two distinct products. All right, so this was an example of a regioselective reaction. What new bond I put depends on which region of my substrate, on which region of my original reactant is going to determine what my product is here. And again, it turns out that only one of these products are actually formed in our reaction here. All right, so this regioselectivity, we got to worry about where we make our new bonds. And so then the next question would be, all right, well, what is our product? All right, and whenever we're trying to figure out details, understanding these reaction mechanisms better, understanding these reactions better, the answer is always going to be to turn to the reaction mechanism, right? That's our full understanding of this reaction that'll help us better understand what products are formed and why. Okay, before we can go on, we're gonna revisit that reaction mechanism that we looked at last time, all right? We chose a particularly simple substrate last time on purpose, so now we're gonna address this regioselectivity business. But before we can do that, we need to take a step back. We need to learn a little bit of terminology here. All right? So first of all, we have this classification system for our carbons. All right, this classification system is really just counting the number of carbon neighbors that a given carbon has. All right, what we call its degree of substitution. So given a molecule, we can look at a carbon, any carbon in that molecule, and we're going to count the number of carbon neighbors that it has. That's what we call the degree of substitution of that carbon. So for example, if I have methane, CH4, this thing has 0 neighbors, right? 0 other carbon neighbors. So this is what we would simply call a methyl carbon, or a 0 degrees of substitution. All right, let's look at propane. That carbon on the very end in propane here has 1 other carbon neighbor. We call these primary carbons. And we use this symbol 1 degree for our primary carbons. If we took that same molecule, propane, but now we looked at that very central carbon there, this has 2 carbon neighbors. We call that a secondary carbon. All right, if we draw a molecule, put a methyl group in the middle there, such that this now has 3 carbon neighbors. That's what we call a tertiary carbon. And lastly, if we have a carbon that's in the middle of 4 other carbons, it's bonded, all 4 of its bonds are to other carbons. So now I have 4 neighbors. Specifically carbon neighbors, that's what we call a quaternary carbon. All right, we use this classification system a lot. It turns out that primary carbons behave differently than tertiary carbons in a lot of circumstances. Let's just practice this real quick. I'm going to put down a big molecule, and you're going to label all of the carbons in this molecule as being either primary, secondary, or tertiary, or quaternary. All right, how many primary carbons do we have here? All right, all these ones on the end here would be considered primary carbons. I can label them with that 1 degree symbol. How many secondary carbons do we have here? These two. And how many tertiary carbons do we have here? This one. And how many quaternary carbons? None. We already accounted for everything. Cool. So we have this classification system for our carbons where we can look at a molecule and we can say, all right, it's either a primary carbon because it's got 1 carbon neighbor, a secondary carbon because it's got 2 carbon neighbors, a tertiary carbon because it's got 3, or a quaternary carbon because it's got 4 carbon neighbors. All right, so this simple classification system for our carbons. Okay, so why do we care about this? Again, we said that the answer behind this regioselectivity is going to be in our reaction mechanism. All right, so let's go back and take a look at our reaction mechanism just to remind ourselves. We kind of looked at this last time. All right, we have our substrate, our organic reactant, our reagent, our inorganic reactant, and our product here. But remember, our reaction mechanism is going to be the step-by-step details of this reaction. And we said that our carbon-carbon double bond plays the role of what? The nucleophile. And our HBr is going to be our electrophile. Specifically, which one of these is my electrophilic site? The hydrogen or the bromine? The hydrogen, right? Our electrophile is relatively electron deficient. The bromine plays the role of what? The leaving group. Awesome. Okay. And then in our mechanism, nucleophiles do what to electrophiles? They attack, right? So our nucleophile is going to attack that electrophile and kick off that leaving group. And this formed this carbocation intermediate, right? We had this bromide ion that was formed, but our organic intermediate here is this carbocation. Remember, a carbocation is a carbon with only 3 bonds. It's an incomplete octet, and it has that positive charge. It's got that positive charge, making it a good what? Nucleophile or electrophile? Electrophile. So in this next step here, my nucleophile was played by my bromide ion with all of its electron density, and it attacked that electrophile, my carbocation. Carbocations don't need a leaving group because they have an incomplete octet, so they can accept electrons readily, and that's how I got my product, my addition product. All right, so this was our mechanism, and we said that this was going to help us explain the regioselectivity, but we got to tie in one more aspect here, and that has to do with this system of classification. It turns out that our carbocations have different stability depending on their degree of substitution. So now we're going to look at carbocation stability, and we're going to rank these from the least stable carbocations to the most stable carbocations. All right, and it turns out that this trends exactly with our degree of substitution. Our least stable carbocations are those methyl carbocations. Remember, it can't be CH4. It can only have 3 bonds to be a carbocation. But I don't have any carbon neighbors, which is what makes this a methyl carbocation. All right. Our next least stable carbocation is a primary carbocation. A little bit better than that is a secondary carbocation. And the most stable carbocation that you can have is a tertiary carbocation. What about a quaternary carbocation? Wouldn't that be even better? It wouldn't be a cation because I have 4 bonds, right? So you can only have 3 bonds to be a carbocation. Just note, if we're filling in implied hydrogens, how many implied hydrogens must be on my primary carbocation? Only 2, right? Can only have those 3 bonds. Likewise, my secondary carbocation can only have 1. Cool. So we learned about this classification of carbons because now we see it coming into play when we're talking about carbocation stability. The methyl carbocations are less stable than primary carbocations, less stable than secondary, and are most stable, at least in this point in the course, are tertiary carbocations. Cool. All right, so then how does that help us to explain our regioselectivity? So let's take that same substrate. All right, and again, I guess just to be clear here, we're going to use our reaction mechanism to explain that regioselectivity. All right, so let's take this thing and react it with what we were using before. What was that, HBr? All right, we're going to do that first step in our mechanism where our nucleophile attacks that electrophile and kicks off that bromide leaving group. All right, in both cases, I'm going to be producing a bromide ion at this step. But I could actually have 2 different carbocations depending on which carbon I say gets that hydrogen. All right, remember, in this reaction here, I'm going to try to animate this here. Right, here's my carbon-carbon pi bond. Well, that carbon-carbon pi bond, that arrow shows a bond breaking reaction. So I'm breaking that carbon-carbon pi bond. And then it swings around and forms a new bond with hydrogen. But the question is, which one of those carbons gets to hold on to that pi bond? I could have it be that one there, right? Or instead, it could be this carbon that reaches around and grabs that hydrogen. And I would get a different carbocation depending. So let's color these orange and green. In my first one, I'm going to put the hydrogen on the orange carbon, which means what should I have on the green carbon? That positive charge. And in my second one, I'm going to instead have my hydrogen on my green carbon, which means that what's going to go on my orange carbon? That positive charge. So from that first step there, following my electron pushing arrows, I could actually draw 2 different intermediates, and both of those would completely follow my electron pushing arrows. I didn't break any rules there. But the question is, which one of these intermediates actually forms? The one on the left or the one on the right? Why the one on the right? Because it's got that more stable carbocation, right? This is a secondary carbocation, whereas this would be one of those primary carbocations, and secondary carbocations are more stable. So this does not form. So then everybody take a second and finish off my mechanism for me. Where is that bromine actually going to go? All right, that bromide ion is going to attack that carbocation. So I specifically have my hydrogen bonded to carbon 1 and that bromide bonded to carbon 2. All right, so just to sort of summarize here, this was our reaction mechanism. If we want to summarize in a chemical equation, this alkene plus HBr specifically yields that 2-bromobutane, where my bromine is on that second carbon. All right, so this is this regioselectivity of this hydrohalogenation reaction, where we can say our halogen is going to be added to the more substituted carbon. All right, and why was that? Because that more substituted carbon formed the more stable carbocation. All right, this feature here where that new bond, my halogen bond, is added to the more substituted carbon. This has this very fancy name. This is a Markovnikov reaction. Clearly named after some Russian dude. All right, where we have our new halogen bond on that more substituted carbon. So that is our regioselectivity of this reaction here. All right, we can say our regioselectivity is that Markovnikov reaction. All right, cool. So let's practice this. All right, I want everybody to take a few minutes to work on these examples here. All right, given what we discussed about regioselectivity, give me the products of these reactions. All right, so I'm going to look at my substrate here, and I got to figure out which carbon, which region of my molecule my new bond's formed on. And since this is this Markovnikov reaction where my halogen's going to prefer the more substituted carbon, I'm going to go through and classify these carbons about this double bond. This one on the end here is a primary carbon. This one over here is a secondary carbon. So where is my halogen going to be bonded? Primary or secondary? Secondary, that more substituted carbon. All right, on this next one here, I'm going to again classify. This is a secondary carbon. All right, but this one over here would be what? A tertiary carbon, so that's where my carbocation is going to want to form. So I'm going to put my bromine on that tertiary carbon. All right, and to be clear, we can draw our hydrogen in explicitly on the other carbon. That's perfectly fine, but we don't have to because hydrogens are implied. All right, now what about this one here? What would this carbon be classified as? This is a secondary carbon. And what about this one over here? What would this carbon be classified as? Also secondary. So is my carbocation going to prefer to go on one or the other? No, they're both equally stable. So then which one do I pick? The answer, unfortunately, is not, it doesn't matter. I know that that's what everybody would love it to be, all right? What we really have to remember is that, and this is kind of hard for when we're doing our pencil and paper organic chemistry, it looks like there's just one molecule here, like one substrate and one reagent. When you're in the lab, you're not dealing with a single molecule. You're dealing with a beaker that contains like 10 to the 23 molecules, some ridiculously huge amount. And the bottom line is 50% of them will choose to form their carbocation over here. The other 50% will choose to have their carbocation over there. So you're going to get a mixture of both possible products. I'm going to get some where my iodide is on my second carbon. Whoops. And the other 50% of my molecules will have my iodide on that third carbon. One of these isn't preferred over the other, so I'm going to get a mixture of both. If they were identical, I wouldn't want to put both of them down, but they're not, right? This is the 2-iodo-propane and the 3-iodo-propane. They're on different carbons. We don't have the symmetry in this molecule that we did in our first example. So I would put both of these products down as my products for this reaction because I had a tie with my carbocations. Cool. All right. So again, we used our reaction mechanism to explain our regioselectivity. There's another aspect of these carbocation intermediates that lead to some funky behavior here, what are called hydride shifts. And these don't happen all the time. They're going to only be seen in specific substrates, but let's put down an example here. All right, let's use HI in our mechanism for fun, changing it up. And I want everybody to do that first step for me in our mechanism based on what we've discussed up until this point. All right, that pi bond is my nucleophile, attacks my electrophile, and kicks off that leaving group. Oops. All right, so in my intermediate here, I have that carbocation. And specifically, which carbon is that carbocation going to be forming on, orange or blue? Blue, and that's because blue is a secondary, whereas orange is a primary. And secondary carbocations are more stable than primary carbocations. All right? But look what's right next door to that secondary carbon. What would we classify this one as? A tertiary carbon. And remember, tertiary carbocations are even more stable than secondary carbocations. So wouldn't it be great if my carbocation could form over here instead of over here? And so that's exactly what happens. There's a hydrogen on this tertiary carbon that is going to shift next door such that our carbocation can now form on that more stable tertiary position. All right, and again, this is what's called a hydride shift. It's when a hydrogen shifts or jumps to a neighboring carbon to form a more stable carbocation. All right, and so for the purposes of simplifying things for our lecture course here, we're going to say that it has to be a direct next door neighbor in order to do a hydride shift. So let's specifically say jumps to a next door neighbor. We're lying to you a little bit. We'll actually see in the results from our experiment this week a hydride shift that occurred over a little bit further of a difference. But for the purposes of our lecture course here and simplifying things, we'll say we only have to watch out for these hydride shifts if our carbocation is forming and its next door neighbor is more highly substituted. So then everybody take a second, given that our iodide ion is floating around here, and now we know what our electrophile is in this reaction. Everybody take a second and tell me what my product should be here, finishing off our mechanism. All right, so that iodide ion's going to attack that carbocation carbon. And so we don't get our iodide on either of those two carbons that were about my original double bond. It's now one carbon over on that even more substituted tertiary carbon. All right, and we're going to see this for all of our mechanisms that have these carbocation intermediates. We got to watch out for these hydride shifts that can occur. Cool. All right, so we got our two electrophilic addition reactions, our hydrohalogenation reactions that are regioselective, and then our halogenation reactions that are not regioselective. We don't have to worry about that same thing, okay? And that's because our intermediate in our reaction mechanism for our hydrohalogenation reactions are carbocations, and we don't see the same thing for our halogenation reactions. Now, we haven't actually looked at our halogenation reaction mechanisms, so that's what we're going to do next. All right, let's just grab this simple example here. Okay, here's our balanced chemical equation. But now we're going to go one step further and look at our reaction mechanism. All right, taking our simple ethene and our diatomic bromine reagent here. All right, and at first everything looks very similar to what we saw before. Our nucleophilic pi bond is going to attack this bromine and kick off that leaving group, that bromide ion. But there's one more electron pushing arrow here that complicates things a little bit. And that is that at the same time that this pi bond is attacking the bromine fights back and attacks that pi bond, or rather attacks that same carbon. And this forms two new bonds, forming a cyclic intermediate here. All right, in order for my bromine to have two bonds, it's got to have two lone pairs and a positive charge. So unlike our hydrohalogenation reaction that has that carbocation intermediate, this has this cyclic intermediate here what they call a cyclic bromonium ion. They gave it a pretty cool name. All right. Now in my next step, I have that bromide ion that was created, that leaving group from my first step. Okay. It's going to go and attack one of these carbons because they have that good built-in leaving group. All right. But importantly, it cannot attack from the same side where that cyclic bromonium ion structure is. It has to do what's called a backside attack, where it attacks from the exact opposite side. Probably didn't think that name through too well, but there's this backside attack where that nucleophile attacks from the opposite side of where that leaving group is. Now in this case, it doesn't make a huge difference as to what my structure is. All right, I'm still going to kind of be good, and when I draw my new single bonds here, I'm going to point them on opposite sides to help illustrate that backside attack. All right, but that's because I chose this very simple alkene substrate here. This backside attack could have very important ramifications for what my product is, and this is what we call stereoselectivity. All right, so we talked about regioselectivity of our reactions. Now we're going to talk about stereoselectivity. A stereoselective reaction is a reaction that produces specific stereoisomers as our products. Okay, I don't know what's happening right now. I didn't remember that this was, is this supposed to be going down today? We're just going to blow past this. Okay, so, okay, great. Sometimes they make us get up and out of the building. I didn't know if that was supposed to be what today is. Cool. We're all mentally ducking and covering right now, all right? Especially since we're talking about everybody's favorite topic, stereoselectivity, stereoisomers, right? Okay, so let's look at a particular substrate where this does matter here, and that would be something like cyclohexene. Okay, so this is our, and we'll just note here, this is our stereoselective reaction, that halogenation. All right, what's up?
You know what to do for the drill?
No.
Okay. Just pretend to do the whole thing. You don't have to exit the building this year.
Okay.
You can stay here.
Fantastic.
Okay.
To be clear, you would duck under the desk, and we're on the 3rd floor, so it would be just fantastic in an all-concrete building. Anyways, we're just going to keep on going here. Okay, so let's do our reaction mechanism. Our nucleophile is going to attack that electrophile, but then we get that really weird cyclic intermediate that forms. All right, but since we have a ring here, we're going to have to draw these bonds as dashes and wedges. So let's think about it. Is it possible for me to have the following cyclic intermediate, where one of those bonds is on a wedge and the other one is on a dash? They're both bonded to that same atom. Can I have one bond pointed up and one bond pointed down and both be bonded to that same atom? No, they gotta be pointing in the same direction, right? So this is illegal here. Instead, I'm going to have to put them both on a wedge or both on a dash. Which means that when my other chloride ion comes and attacks, again, it's got to do so from the opposite side of where that leaving group is. So if I'm going to be consistent here with how I've drawn things, that means one of those chlorines is going to end up on a wedged bond. And the other chlorine is going to end up on a dashed bond. All right, using that cis-trans designation, we produced a specific stereoisomer here. Which one? That trans stereoisomer was produced in this reaction here. All right, so we get this stereoselective product. All right, so if we were going to do our balanced chemical equation here for this reaction, okay, we would have to be good. And we would have to include this stereoselective product. We couldn't just put those chlorines on those straight line bonds. We would have to put them on dashes and wedges. And not only that, but I chose one particular structure where they were both on wedges, but I could have put them instead both on dashes. So we're going to get a mixture of these two trans enantiomers here, and I would have to list them both as my stereoselective products. All right, importantly, I get no cis product out of this, so I have to include these dashes and wedges, my stereoselective reaction. All right, and I'm going to include both enantiomers, the RR and the the RR and the SS. Okay, so this is this stereoselectivity, a reaction that produces a specific stereoisomers as products. I don't get a mix of all stereoisomers. I only get my trans stereoisomers out of this reaction. So since I have this stereospecificity, I have to be good and show that with these dashes and wedges. All right, we said that our halogenation reaction was stereospecific. To be clear, a reaction that would not be stereospecific is our hydrohalogenation reaction. All right. If we took a similar reactant here, I'm going to have to make it asymmetric because of this particular reaction. All right, let's say I even started out, so we have the stereoselective reaction here, or not stereospecific reaction. I'm going to react this with HI. Everybody take a second and draw me my intermediate in this reaction. Fill in our mechanism arrows. All right, importantly, there is some regioselectivity. So I do want to put my carbocation on a specific region in this molecule, on that more substituted tertiary carbon here. And my iodide is going to attack that carbocation. All right, but importantly, we said how many bonds does a carbocation have? 3, which means what is the hybridization on that carbocation? sp2, which means it's what geometry? Trigonal planar, right? So these carbocations are sp2 hybridized and thus trigonal planar. And if it's trigonal planar, that means it's nice and flat. So my iodide molecule, 50% of them will attack from one side, 50% of them will attack from the other side. So I'm going to get this 50-50 mixture of my possible stereoisomers. %, I guess that was the bad choice. 50% would have that iodide attacking from the top. The other 50% would have that iodide attacking from the opposite side. And what do we call it when we have a 50-50 mixture of both possible stereoisomers? A racemic mixture, right? So for these reactions here, we're always going to get a racemic mixture. And our racemic mixtures, we don't bother specifying our stereochemistry for. We would just draw our racemic mixtures as one structure using those straight line bonds, right? Our racemic mixtures we can represent with straight line bonds. Okay, so our stereospecific halogenation reaction, we only get a subset of our possible stereoisomers, so we have to specify the stereochemistry of our products. Whereas our hydrohalogenation reaction, we always get a racemic mixture, even if we create a chiral center like we did here. We always get a racemic mixture of both possible stereoisomers, and we can just represent that racemic mixture with our straight line bonds, one structure using our straight line bonds. All right? So we got these two different addition reactions that we covered, our halogenation reactions and our hydrohalogenation reactions. For one of them, we got to worry about the regiospecificity, specifically where that new halogen bond is going to be going. We don't have to worry about regiospecificity for our halogenation reaction, but we do also have stereospecificity. We don't have to worry about stereospecificity for our hydrohalogenation reaction, but we do have to worry about it for our halogenation reaction. All right? So for your homework this week, there's sort of two different assignments that have you practicing these reactions. One where it's kind of this simple best case scenario where you don't have to worry about things like stereospecificity or hydride shifts, and one where you do have to watch out for those more special case scenarios, all right? And it'll be pretty clear in the instructions. There's also what are called like these tutorial assignments that I have where it walks you through how to draw your products correctly, for example, to make sure that you're getting all of your regiospecific and stereospecific products when you're doing these particular reactions. Cool. All right. And we're going to pick up, we're still going to be talking about alkenes next week, and we're going to introduce a few more reactions of alkenes. All right. Now, who would like